In this lecture, I'd like to wrap up our discussion of modulation techniques. And in doing so, I would like to come back to a couple of ideas that we talked about in the previous few lectures. One is the idea of additive noise. So especially in the previous lecture, when we were talking about concentration shift keying, we talked about what you could do is you could send, for example, 0 molecules or n molecules. And what we mentioned is that obviously if you send 0, the number received is always 0. So if x equals 0, y necessarily equals 0 deterministically. So if you send nothing, you receive nothing. At least in this world in which there are no molecules other than the ones we send using this symbol. Subsequently, if x equals n, then y is distributed binomial. With probability of arrival, we talked about it last time, but it's PR of TS, and the number that we send is n. So I guess we could say n PR TS. And this is approximately Gaussian with mean n PR of TS and variance n PR of TS times 1 minus PR of TS. Okay, so from now on, I'm going to call this the fundamental mean is mu. I'll call it mu naught. That is the fundamental variance. I'm going to call that sigma naught squared. So this is equal to Gaussian n mu naught n sigma naught squared. Two things to notice about this. First is, well, three things actually. First is these are consistent. So if n is 0, y is deterministically 0. So that's mean of 0 with variance 0. So that this actually makes some degree of sense. Second thing to notice, so let me actually write this down. First thing to notice, if n is 0, this is still consistent. In the sense that if y is distributed Gaussian with mean of 0 and variance 0, that is deterministically 0. Second thing to notice, there is a sense of additive noise here. So in other words, if y is distributed Gaussian, mean n mu naught, n sigma squared naught, then this is as though y could be said to be equal to some signal x plus n, where x is in 0 mu naught, 0 n mu naught for the sake of binary, or in the case of binary. We could also go with Emery, so we could take x in, as long as they're uniformly spaced, we could say x in 0, n mu naught, 2 n mu naught, and so on, up to, let's call, if it's emery, we could call this m minus 1 n mu naught. So this would be emery. So that looks cool. What this means is that for practical purposes, this is something like additive noise, additive Gaussian noise, where my signal is determined by the mean of the Gaussian. So in other words, I can take that mean out and then I end up with zero mean Gaussian noise. However, the third thing to note the noise is data dependent. Remember this, y, if we say y is equal to x plus n, where x is in 0, let's just do the binary case for the time being, 0 n mu naught for binary. What is n? N is then distributed Gaussian with 0 mean. So far, so good. But its variance, if I come back to the previous page, its variance actually depends on which one we send. If we send 0, the variance is 0. If we send n, the variance is n sigma naught squared. So the variance is actually dependent on which value of x we choose. So n is distributed either Gaussian, mean 0, variance 0 for x equals 0, or Gaussian, mean 0, variance n sigma naught squared for x equals n mu naught. Similarly, noise would be data dependent if you used memory scheme. Should be clear how that works out, but I'll let you work that out on your own. So that is interesting. We don't usually run into additive noise schemes where the noise is data dependent. So in other words, the stronger the signal, the stronger the noise. So you saw with 0 signal, if you send no molecules, you're guaranteed to get no molecules. So 0 signal means no noise. And as the number of molecules released increases, the amount of noise increases, and that's because each individual molecule has a random chance of ending up at the receiver. So the more molecules you have, the higher the variance in the signal. So we often, in a conventional noise-independent variance kind of arrangement, we might have this for on-off keying. We would have something like this. Sorry, let me draw that a little bit. If we have a signal at 0 and n mu naught, if the noise is data independent, then we would normally have a Gaussian surrounding this at a certain variance and a Gaussian surrounding this at a certain variance. So this would be if noise were data independent. In our case, noise is data dependent. Molecular communication. And writing something similar over here, we still have a Gaussian around n mu naught with variance n times sigma squared naught. But around 0, we actually have a delta function. There's no variance in the signal around 0. And if we generalize this, we might have something like this. So 0 n sigma, excuse me, that's n mu naught, 2n mu naught, 3n mu naught, and so on. At 0, we send 0, we get 0. This is just a delta function at 0. N mu naught. This is a narrow Gaussian. 2n mu naught. This is a slightly wider Gaussian. 3n mu naught. This is an even wider Gaussian, and so on. So we can see that the practice. Well, I'll just leave this as a thought for you. In data independent noise, we often space signal points uniformly, which leads to uniform probability of error. So for instance, if I go back to the previous page, because of the symmetry of the Gaussians, the weight, so here's the threshold here, the weight under this tail would be about the same as the weight under this tail. That's no longer true over here. If I space them uniformly, the errors that I get if I send a 0 are different from the errors that I get if I send an n mu naught and 2 mu naught and so on. So it might be a good idea. So if you want uniform PE, in concentration shift keying, you should have non-uniform spacing. And this is because, again, the noise is additive, but not signal independent. In other words, you get the more signal you send, the more noise you have. This is a unique feature of molecular communication. Another thing very important that I want to talk about here that we have avoided up till now, in fact, we deliberately avoided talking about it, but if you've thought about it, you should see that it's an obvious problem, is intersymbol interference. So far, we have avoided talking about reusing the channel. So for example, consider concentration shift keying at time 0. So here I am going to draw a timeline. So this is time. So at time 0, let's say I send a 1. So in other words, I send n molecules. Then at time 1, let's say, in arbitrary units, this will be my symbol interval. Between time 0 and 1, it's a non-absorbing receiver, so I can certainly count how many molecules arrive. The probability of those molecules arriving will decay over time. But let's say at time 1, I send 0 molecules. And what I'm going to do is in these symbol intervals, I'm going to try to detect how many molecules arrive in that interval, and I'm going to relate that back to the symbol that was transmitted here. So for instance, I'm going to observe the receiver in here and try to figure out if 0 or n were sent. Same thing here. So you can see the problem, which is that some of these molecules could arrive here. And in fact, this is even worse in CSK. It's non-absorbing. So when I send those n molecules, they're still floating around. So they float around basically forever. And there will be some probability that they'll arrive here, 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 and so on. They're never absorbed. Even if I, at some point, observe all n, they could still come back later. So this is classic intersymbol interference. So intersymbol interference is a serious problem. Molecular communication. So what I want to do here for a minute is characterize the problem and come up with some solutions. So one simple solution would be to wait a long time between symbols to allow the medium to clear. However, you could be waiting an exceptionally long period of time. This is diffusion. So you can imagine, I mean, informally, you can imagine a large tub of water, you drop some dye into it and look at one small area within that tub of water. It would take an exceptionally long time for the dye to dissipate to the point where you can't see it anymore. So this is inefficient. It's quite inefficient. In terms of the bit error rate, or excuse me, in terms of the bit rate. We'll say information rate. In other words, if you're always waiting an outrageously long period of time for the channel to decay back to where it was before, you'll transmit information at an extremely low rate. Another solution is to explicitly count for ISI in modulation detection. And there are plenty of ways to do this. Lots and lots of techniques have been devised over the last 50 years to deal with intersymbol interference. And what we're going to do, just to get a handle on the problem, the first thing to do is to understand. So we need to understand the impulse response. channel. All right, so in order to do that, let's remind ourselves of what the channel looks like. So recall, we have a 1D channel, non-absorbing. So this is concentration shift keying. You can, the concept of intersymbol interference also exists in timing channels, but it's a little different conceptually. But we're just gonna deal with concentration shift keying here. So 1D channel, non-absorbing receiver. And what we have is we release molecules at the origin. This is the transmitter. And my receiver is from A to B. And basically what I'm doing is I am counting, count the number of molecules in R at each time. So suppose I am interested in the expected value. So let me say I count the number of molecules R at each time. I'm going to call that Y of t. Suppose I'm interested in the expected value of Y of t. And how do I get that? Well, each molecule, each released molecule as we've mentioned before, the way we analyze this, we say each released molecule can be within R. So I'm going to call that a 1 or not. I'm going to call that a 0. I mean, what we're doing is we're counting. So if it's within R, then I count it. So that's a 1. So that's a 1. And if it's not within the region, it's a 0. So I count that as a 0. So basically what I need is at each time, the expected value of Y of t is, if for one single molecule, it's just that, it's just the probability of being in R at t. That's it. Now, if I think about an impulse response, I'm going to hand wave a little bit here, but it's straightforward to construct a rigorous argument along these lines. If I'm interested in the impulse response, then we release a huge number of molecules. Each molecule will propagate independently. And the average number observed time t is, it'll be n. If I release n, it's n times PR of t. Normalized, if I normalize that to the number sent, basically what I'll have is, actually this is equal to the expected value of Y of t. Here, the expected value of Y of t divided by n. N is just deterministic here. That is PR of t. And by the law of large numbers, if I have, actually, I don't even need the weak law of large numbers. Let me back up here. The variance of y of t over n is going to go to 0 as n goes to infinity. So the deterministic impulse response will be just PR of t. Okay, I hand waved a bit there because I don't want to spend a giant amount of time on this, but hopefully you can see through this hand wavy sketch how to construct a more rigorous argument about it. But the idea is that basically the larger the number of molecules you have, the closer you're going to get to a deterministic impulse response of PR of t. So that's interesting. Basically, that means concentration is going to decay deterministically, and that this is something that we already know intuitively, and we've also proved it in a previous lecture, that the count basically becomes concentration as the number of molecules grows. I'm going to post a notebook related to this so that you can see exactly how it works. I just want to point out, what is PR of t? In fact, we actually saw what PR of t was in the previous lecture, but just to go over it once more, again, I released from the origin, and I want to know the probability that my molecules between A and B at any time the Brownian motion is distributed Gaussian with mean 0, assuming the initial position is 0. So it's mean 0 and variance 2 dt. So that means the probability of between being A and B, well, the probability of being less between 0 and A is 1/2 ERF A over root 2 dt. The probability of being less than B is 1/2 ERF B over root 2 dt. And so the probability of being between A and B is just this minus that. So in other words, it's the probability of being in here minus the probability of being in here. And that is PR T. So that, quite simply, gives you your impulse response. So this is the impulse response. The CSK signal. You will see this on the notebook if you try it. But one thing that I want to say about it is that it decays very slowly, even more slowly than the Levy distribution. So this impulse response decays very slowly. Just to sketch an example, it'll tend to go like this. I'll have a nice peak, and it will just decay very, very slowly. And again, look at the notebook for an example, and you can construct an example by yourself if you want. So ISI mitigation. So in other words, if you were waiting for this to decay down to 0, so you could send another symbol, that's not feasible. So there are many techniques, physical techniques, mitigate ISI, it can include inducing drift. So notice that this impulse response is drift free. And if there were drift, that would actually make it decay a lot more swiftly. So you could induce drift, you could increase drift, like increase circulation, use a fan or something. You can force molecules to decay. So in other words, you could release an enzyme that breaks down the signal-bearing molecules, or there's an example, we talk about it if we have time later. There's an example of communicating using acids and bases, so that if you want to send a 1, you send an acid. If you want to send a 0, then you send a base, which not only sends a 0, but also wipes out the acid. Many other techniques also exist. So that about sums up what I want to say about modulation. So now we have a good idea of the basics of molecular communication, the physical basis, and how to send very simple signals. We can relate them to concepts that we're already aware of, including maximum likelihood detection, probability of error, intersymbol interference, and so on. In the remaining lectures, we're going to talk a little bit about how to apply these in terms of advanced techniques. So the remaining lectures will be a little less technical, a little less mathematical, and more looking at. But there will still be some technical material. I do want to address MIMO, but some of the other material will be a little more qualitative rather than quantitative.